Hi all, our standard for this video is areas and volumes. Our objectives include measurements of 2D figures, measurements of 3D figures, and then we'll find the area of the shaded region for some. We start with measurements of 2D figures and some definitions. The perimeter for a two-dimensional shape is the total distance around the shape. Note here, for figures with straight line boundaries, we can just add up the lengths of all the sides. For a circle, we need a different formula. The perimeter of a circle is called its circumference, and is calculated using the formula C equals 2 pi r. Definition: the area for a two-dimensional shape is the space enclosed within the perimeter of the shape. So for number 1, we want to find the perimeter and area for the following figures. For our first figure, we've got a rectangle in the first quadrant here, and we can see 4 units across the bottom, 3 units up the left and right sides, and 4 units across the top. So if we do on our perimeter, we can add our 4, our 3, our 4, and our 3, which gives us 8 and 6, so 14. And really, we remember, hopefully, for a rectangle, our perimeter is 2 times the length plus 2 times the width. So we could also have done this with a 2 times 4, say, and a 2 times 3. So 8 and 6 there would still give us 14. For the area, I put it on the grid just so we can see kind of where it comes from. But we do know it's length times width for a rectangle, which is going to give us our 4 times 3, or we want to do 12 units squared, and really this is just 14 units. I'll write it all out there. We got some time, but hopefully we can see them in the space. We went by ones in both the X and Y directions, so that's our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 square units there. All right, and so we can at least talk about where the formulas for some of the other ones come from based on those. For the triangle in B, we can see a 4 across the bottom, a 3 up that left side, and those are both legs. We went with a nice right triangle here, which means we know how to find the length of the third side. So our perimeter is going to be a 3 plus 4 plus something. If we do call this one C, because hopefully that's familiar, we've got our legs squared plus our other legs squared, giving us our hypotenuse squared, our Pythagorean theorem. We can put in a 4 squared plus our 3 squared gives us our C squared. 16 then plus 9 will be C squared, or 25 is C squared, which means that our C is 5. So we can add that 5 there, and we found our third side. 5, 9, 12. For the perimeter of our triangle, we can put 12 units again. Right, we weren't given inches or feet or centimeters or anything, but it is important to keep track of the units when you're working with perimeters, areas, volumes, all these things. So we know if we're in regular units or square units like we were for the area, or when we move up to volumes at third dimension, we'll get cubed units. Our area for the triangle, you might remember the formula 1/2 base times height, or 1/2 length times width. And really what I wanted you to see is that it's just half of the rectangle here, right? So we can still see some of those full squares, 1 square, 2 square, 3 square, and then really these ones probably go together. So here we'll call it 4A and 4B, right? Looks like those make a full a full square there, and then we'd have this one 5A with this tiny guy up here. This is 5B, and then we got 6A and 6B in here would go together to make 1. So it looks like about half that rectangle, and we can see if we did draw on our opposite sides, we'd have the whole rectangle there. So that diagonal of the rectangle is going to cut it in half. For our area here, we get a 1/2 of 4 times 3, which is half of 12, or 6 units squared. For 1C then, we've got a trapezoid. We can see along the bottom, we've got 10 units. Along the top, we're only 2 units. And then we've got to figure out those lengths of the sides there if we want the perimeter here. So our perimeter, so far we've got a 10 plus a 2 plus some other things. We can call them C and D for fun. For C, what we want to take note of is that we can create a right triangle here. And so that one would have a base of 4 and a height of 3, which means we don't have to compute again. It's got a length of 5. And we can do the same thing on the other side. We have this 4 with a 3 up the top, and our D there is also going to be 5. So our perimeter, if we get rid of C and D here, would be 10 plus 2 plus 5 plus 5, which is going to give us 22 units. And the point of drawing those out and not giving you those two sides is so you can see for the area here. If you don't remember the area of a trapezoid, which is 1/2 of base 1 plus base 2 times the height, you can always just divide it into more familiar shapes. We know the area of this triangle is 6. We know the area of this triangle is 6. I was going to put units squared there. We just did this up top. And we know the center rectangle is a 2 by 3, so that's also 6 units squared. So our area would be 18 units squared. So if you remember the formula, it can help, but going to those easy shapes is also good. Let's do it here with our formula. We had a 1/2 of a 10 plus 2 times our h here. Our height is just 3 there. You can see in the middle from bottom to top. And so we get 1/2 of 12 times 3. And that 6 times 3 gives us those 18 units squared, or square units that we saw with our 3 cuts. All right, for D, we've got our circle. We can see it's a circle with center 0, 0, and radius r equals 5. So for our perimeter, or our circumference, we've got a 2 pi r, which is really going to be a 2 pi times 5, or a 10 pi. For our area of a circle, we've got that pi r squared formula, which will give us a pi times 5 squared, or a 25 pi. And here we can throw our units and units squared on there, so we don't forget. All right, for 3D figures, we start with a definition. The volume of an object is the space occupied within the boundaries in 3-dimensional space. And we also have that the surface area of an object is the total area on all surfaces of a 3-dimensional figure. So we want to compute the volume and surface area for the following figures. For A, we have a cube with a side of 6 inches. So for a cube, we have our volume. Volume of a box would normally be length times width times height. Here we can write that over for B. Length times width times height, right? Length times width was our area. When we bring our 3rd dimension height in, we've got to multiply by that height as well. And so for the cube, where length, width, and height are all the same, we end up just calling it s cubed, our side length cubed. All right, for our surface area, we can draw out a little net over here. If I unfold this box, I pull this left side down to the left. That's this guy here. This is my bottom. I can pull the front face down this way, back face down over there, and then the top and right side are going to unfold together. I think there's 20-something, 11, maybe, I don't know. There's a bunch of different ways to write a net for a cube or a box here, but this is hopefully the easiest one to think about. So that's our bottom, that's our top. And all these have side lengths of 6, right, no matter where we go. So we can see, hopefully, 6 of the same figures, all with side lengths of 6. And so for our surface area, we can see 6 different surfaces, all with the same area, and that area is going to be s squared each time. So we have 6s squared, or 6 areas that we're going to add up. For the volume, for this one, we have a 6 cubed, which is 216 inches cubed here. And I guess 6 isn't the best one to do there, because then we get a 6 times 6 squared here for each face, which gives us a 6 cubed, or a 216 again for our surface area. So inches squared here. All right, for the box, we won't get the same answer for each, so let's do that one. Our volume, our length times width times height, is a 22 times a 3 times a 4.1. The 22 and 3 gives us 66 times 4, 240 and 24, 264, and then a tenth, 6.6, 270.6. That's our inches squared. For the surface area, we can't draw out that nice big net, but we can see hopefully two of the same faces in the front and back. So we have two areas that would be, that's our length and our height. So two lengths and heights. We'd also have a right side and a left side. Those ends are 3 by 4.1, or our width times our height. So two WHs. And then our top and bottom. Top we can see, bottom we can't down there. But those are our length by our width, so 2 LWs. So when we sub in, we get a 2, our length is 22, our height is 4.1, and plus a 2 times our width is 3 times our height, 4.1, plus 2 times our length, 22, times our height, 3, gives us a 44 times 4.1. We get 160 and 16, 176, plus a tenth of 44, so 4.4, so 180.4. Plus, we get a 6 times 4.1, or a 24.6. Plus, we get a 66 times 3, or 44 times 3, or 66 times 2. So how about a 132? And altogether, that's going to give us 337 inches squared for our surface area. All right, so we got our box. For C, we're looking at a cylinder with a diameter of 24, so we want to make sure we pay attention to that. That's our diameter, which means our radius is 12 inches. And so what we want to think for a lot of these solids, we have the area of the base. And if we stack up tons and tons of circles on top of each other, like stacking up poker chips or coasters or something, if we multiply by the height, we get the volume, because we have the space taken up in one disk times how many disks there are. So our volume here is just going to be the area of the base times the height. Since our base is a circle, it's a pi r squared times our height, h. And then for the surface area, if we do think I like peeling this thing apart, if we unroll it, we'd have the two circles, top and bottom, with this big rectangle strip in the middle that we'd fold up to make most of the cylinder, or part of that can. And so for our surface area, we have two circles, so 2 times pi r squared, right, the area of those circles, plus we can see the length here, since it's unrolling the circle, is our circumference, 2 pi r, and then our height. So, and a 2 pi r h there. So if we do our volume, we need our height and we need our radius. So we've got a pi times 12 times 20. And that 12 needs to be squared. So we get a 20 pi times, let's say 12 squared was 144. We're just multiplying by 2. So we get a 288 in our 0. So 2880 pi inches cubed. For our surface area, we got a little bit more work to do. We've got a 2 pi times r squared, that 12 squared, plus a 2 pi, 12 for r, 20 for h, which is going to give us, let's see if I can fit stuff down here. I don't know if I accounted for that picture. So the 144 with the squared, so 288 pi. And then we've got a plus 20 and 12, or 20 and 24 is probably easier, a 480 pi, which together gives us 680, 768. You can check me, inches squared. That sounds all right. And for D then, we can think kind of the same way. We've got this nice solid, or it's called a triangular prism. We have the two triangles as our bases, and then we have a height, like we're stacking up a ton of triangles. So our volume here, our area of the base, is that 1/2 base times height for the little triangle, times, I'll call it a big H for the height of the whole figure. All right, so this again is just our area of the base. And then we want to multiply by the height. And really we could do that over here as well. The pi r squared is just our area of the base. And we're going to multiply by the height. And then our surface area, maybe a little bit harder to see. I can fit some stuff over here on the side. Let's see if we can see our surfaces. We've got two of these triangles. so times 2 with a 6 and an 8. And then because of that, right, the 3 sides, so 6, 8, you can do your Pythagorean theorem, or if you remember your triple, the 3, 4, 5s or 6, 8, 10s that scale up from there would give us our hypotenuse here of 10. Gives us 3 different faces, right? One of them over here, I didn't even try and draw it right, but it's got that 6 by our height of 15. And then the face way in the back there would have that 10 hypotenuse and our height of 15 still. And then the one kind of over here in front of us, a little bit bigger, is the 8 by 15. So we've got 5 different pieces we're adding up for the surface area. We've got twice the area of that base, so twice 1/2 of our little base times height for our triangle. Plus we want our 3 bases, so here we can call it A times height plus B times height plus C times height for our A, B, C, and sides of our triangle. You won't have to remember a formula, we're just getting the pieces here. And so for our volume, we have a 1/2 our base and height, we're 6 and 8 for that triangle, and then we're going to multiply whatever that is by 15. So we get a 1/2 of 48, so 24. 24 15s, each 4 is 60. We got 6 of those, so 360 inches cubed. For the surface area, we can just keep working down here. 2.5 would just make 1, so we got our base times our height. That's our 6 times 8 for that triangle. Plus our A, we can think the small side, 6 times our height 15, plus our base, our other leg, 8 times 15. So I guess I didn't want to use B for both, but just to get our point across there. And then we had 10 for the third side there, times our height 15. So we have our 3 areas of those rectangles. You can see the 6 times 15, 10 times 15, 8 times 15, and then 2 of those triangle bases. And so that gives us a 48, a 90, a 120, and a 150. And if we add all of those up, we get a 360 and 48, so a 408 inches squared for our surface area. All right, fun. We move on to some very important ones for calc. All right, so for E then, we've got a cone. Our volume is just 1/3 of the cylinder, so 1/3 pi r squared h, or you'll see it a lot of times as pi over 3 r squared h. But for the surface area, we've got the base pretty easily. That's just a circle, so pi r squared. Plus, for the outside, that would make like the, I don't know, cup part, if this was a paper cup, that we'd wrap up to make the cone. We need a pi r and a L, which is what they call the slant height, so the length here up the side. And so we can pull out that triangle, right? We can view this as we've done before as a right triangle with that point at the center of the base all the way down to the point or tip of the cone. And so we just want that right triangle. We used it for similar triangles before. Here we're going to use it to get our slant height L. We can see 9 and 17 for our 2 sides, and so it's a Pythagorean theorem thing. Our L squared is equal to a 9 squared plus 17 squared, which is going to give me an 81 plus 289, and that's 370. And so L is going to be our square root of 370, which 37 and 10, 37 is prime, we can't break down, so we'll just leave it like that and hope things work out well for us. For our volume computation, we've got a pi over 3. Our r would be a 9 squared, and then our h is a 17. So we've got 9 squared would be 81, but if we take one of those 3's away, we get a 27 pi, and then we still got to multiply by 17 there. 27 and 17, give me a 459 pi. We've got meters cubed. And then for my surface area, I want to plug some stuff in. I've got a pi, my r is 9 squared, and then plus I've got a pi, a 9 for r, and that root 370 we just found for L, my slant height. So not a whole lot we can do to simplify that one. We'd get an 81 pi plus 9 pi root 370 units squared, or what do we have, meters squared. Cool. All right, for a sphere, we have a volume of 4/3 pi r cubed. Right, that cubed is for our 3 dimensions. Over there for the cone, we had the r squared times h. Those were our 3 dimensions. And then our surface area, we bring that 3 down, and we get a 4 pi r squared. So my r is 3. I've got that one here. Hopefully this is a little easier computation. 4/3 times pi times 3 cubed, which is 27, but we'll divide by 3 to give us a 9, and that gives us a 36 pi, what are we in inches cubed here. And then for our surface area, just a 4 pi times 3 squared. So a 9 and a 4 gives us a 36 pi inches squared there. Fun. All right, for the last section, we are finding the area of the shaded region. For number 3, find the area of the shaded region. We're looking at A. This takes you back to hopefully middle school or something, but is leading into something we're going to do a lot in calc. To find the area of the shaded region, we can see that we have a rectangle with a circle inscribed in it, and that circle is not part of our shaded region, so we can get the area of our big box, which is 4 units by 2 units, and subtract off, so area rectangle minus area of the circle that's not shaded in. And so our area of the rectangle is a 4 times 2, minus our area of the circle would be a pi times, our radius is just a 1 there, right, from the center, 1, 0, 1, either down to the origin or up to 0, 2 is a distance of 1 squared. And so we get an 8 minus pi, we can say units squared for our area again. All right, for B, we can see big triangle and small triangle. And so what we want to think, the area of this big triangle I put in red, minus the area of this little unshaded triangle will give us the area of the shaded region. So those are easy ones to compute. So we can put area red triangle, RT, would equal 1/2. Our base is 5, our height is 3, so 15/2. And we want to subtract off that area of the bottom triangle, or blue triangle, which is a 1/2, 5 times 1 for our height, which gives us just a 5/2, which is going to give me a 10/2, or 5 units squared for my area. All right, a few different ways we can do C. Depends on how you see it. I'm thinking we've got, similar to the last one, but a big triangle here with my base on the y-axis now, and then my little triangle over there as well. And so then my area for the red triangle would be a 1/2. My base, we can think 3. By my height up that x-axis is a 4. 12 over 2 would give me a 6. And we're going to subtract off my area of the blue triangle, which was a 1/2 times base of 1, height of 4, which gives me a 2. And 6 minus 2 there will give me an area of 4 units squared. That's it for some area and volume formulas you will hopefully see here and in calc. Go try some stuff. Reach out if you got questions.